I'm Michael Rabin, talking to you from the Hebrew University in Jerusalem. I want to thank the organizer of this birthday celebration for having invited me to be one of the speakers in honor of Dick Karp. Dear Dick, it's your 80th birthday, and I want to tell you that becoming 80 is not the end. It's not even the beginning of the end. It's only the end of the beginning. And you and we all have many happy and active years ahead of us. Dick and I, we have many years together, going all the way back to the 1960s at IBM, where we first met. And we had many unbelievably interesting conversations, both about computer science and general subjects together. So it is really a very happy moment for me not to see you directly, but to be via the internet, to be with you here again. My lecture today is going to cover some of our joint work and later on some of my own later work that was done, which I'm going to describe just as proof that even after 80, you are of course extremely active, and so am I. So in 1980, I was visiting Berkeley and came across the problem of string matching. Tzvi Galil had a new algorithm for string matching, which reduced the number of required registers from about n for a pattern of length n to a fixed number of registers. I thought that there should be an efficient and simple randomized solution for that new result. And so I had a certain solution, and I came and told you, Dick, about it. You immediately had an important simplification, and we went on to write a paper that appeared in 1987, and which people tell me became a classic. So let me briefly describe the problem. Namely, a sufficient randomized string matching algorithm, not even one, but actually a family of algorithms. So you have a string x, A1, A2, x, A1, A2, up to AN of symbols, for example, zeros and ones, and that's one example of a pattern. And you have another much longer string, y, B1 up to Bm, which is the text. And the question is, where in the text does the pattern appear? So here is a small mini example. You have ABBA, there's no match here, no match here, no match here, but finally there is a match. So the exercise is to find all indices k such that x, the pattern, matches the kth stretch of n symbols in the text. Now, this problem had already a long, rich history. The first important result is due, not surprisingly, to Knuth Moritz Pratt in 1977. Just one example of the many outstanding and nice results due to our friend Knuth. And they gave a solution that required ON registers for fast implementation. As I mentioned before, in 1980 in Berkeley, Galil and Cyphers found a solution published in 1981 which required just a constant number of registers. This was a deterministic solution and involved a complex algorithm. In 1978 in England, Baker generalized the deterministic string matching to general arrays, multi-dimensional arrays. So, for example, you can look for a pattern which is a rectangle of A's and B's in a text which is a larger rectangle of A's and B's, and similarly for higher dimensions. Vyshkin in 1985 gave parallel version for these deterministic algorithms. So now I come to the Karp-Rabin historical solution for that problem. You choose a random prime in the range between 1 and n times m squared. That means, if you think about it for a moment, that this is actually a rather small prime. Now we consider in this example the x and y to be a pattern in text consisting of zeros and ones. The AI and the BI are either 0 or 1. We start by computing A, which is the pattern mod P. In other words, a number smaller than P. And we take the first stretch of n bits in the text, and we also consider and compute and consider its residue mod P. Now, if A equals A1, there is a match in location 1 with high probability of E being right. Now we test the location, namely the text, in this way using mod P residues bit by bit. An important feature is that the update of the fingerprint, so-called, of the ith stretch of n bits in the text can be updated from AI to AI plus 1 very easily, as is seen in the first 2 lines of the slides shown now. Now, if in fact there is a match, then of course there is going to be agreement of the fingerprints. However, at the same time, if the fingerprints agree, there is a match with very high probability. We call this methodology fingerprinting. Now, continuing the description of Karp-Rabin algorithm, there are efficient updates, 1 modular multiplication, 2 modular additions per update, 1 move forward within the text. It needs only 5 registers for holding locations and prime in memory. Correctness I have already described before. Karp-Rabin easily and naturally yields all previous results and in many instances even improved forms of those results. Many stringology results are uniformly and easily solved by the KR fingerprinting method. In 1981, I introduced fingerprinting using irreducible polynomials, which is widely used also for many security problems. Now, as I said in my introduction, becoming 80 is not the end of one's life and career. I want to say about the previous work with Descartes that all of life's problems should have such elegant and easy solutions. Coming now to new results. I said in my introduction that becoming 80 is not the end. Descartes has amply proved it by his work in recent years. I want to describe some of my own work and work with others in the same vein of being able to innovate even at what is considered, quote, advanced age, unquote. So this is efficient zero-knowledge proofs. And the work I'm going to describe goes back to the papers RST 2007, RMMY 2012. That's when these papers appeared in print. And then I'm going to give another important application due to Silvio Micali and myself. So the basic concept is random split value representations of values. A value x in the range 0 to b minus 1, which is the finite field ZP, where p is actually a small quote-unquote prime, let's say at most 2 to the 128, in other words, fitting into 1 or 2 computer words, and our operations are addition and multiplication mod p. Now suppose we have a value x and we represent it random split value representation by a vector, by a random vector capital X uv. And the value of that vector is going to be u plus v mod p, which should be lowercase x. How do we construct that random representation? We choose the first coordinate u randomly from in the field ZP. And then we take the other coordinate v as x minus u mod p. So obviously u plus v mod p is x. Now note that each coordinate by itself is completely random, and if revealed on its own, gives us no information about the value x in question because of the complete randomness of u on the one hand and v by itself on the other hand. And Michael Rabin's 11th commandment is that in this split representation, you never reveal both coordinates. Always reveal at most one, either the left or the right coordinate. Now, we use any kind of commitment function for values, and the split value commitment to the vector capital X is the commitment to the value u, comma, commitment to the value v. And those commitments are used later on, immediately will be used in the zero-knowledge proofs. So now, it is a fact demonstrated in the papers I quoted before that there are efficient zero-knowledge proofs for the following. if a prover has split value and has posted split value commitments to X, split value commitment to Y, and split value commitment to Z, and these are posted for a verifier, the prover can efficiently, very efficiently, prove in absolute zero knowledge such statements that the value of X plus the value of Y is equal to the value of Z, or in another case, that the value of X times the value of Y equals the value of Z, or in yet another case, that the value of X is smaller than the value of Y. Now, having the power of zero-knowledge proofs that I described in the previous slide, we want to generalize this to general straight-line computations, acronym GSLC, Generalized Straight-Line Computations. So we can assume a very general situation where there are input values from x1 up to xn, lowercase x1 up to lowercase xn, from players, which could be bidders or could be something else, p1 up to pn. Now, an evaluator prover creates a generalized straight-line computation which has outputs x lowercase l, a function of the inputs, up to xl plus 1, a function fl plus 1 of those inputs. For example, the outputs could be the ordering of these inputs. So he looks at the inputs and he creates the generalized straight-line computation for other problems also, so that for all m greater than n, there exist two previous indices I and j, such that xm is either the sum of xi and xj mod p, or the product of these two, or xm is the truth value of the relationship xi less or equal to xj. Other operations, more general operations, are also treatable. The GSLC in question, of course, is adopted or is made to solve the problem which has to be solved, and we are going to have examples in the following. Now, the approach suggested and developed in the papers mentioned here work directly with small residues mod p. There is no need even for solving problems like proving x smaller than y to go down to the bit value. There is no need, as some solutions to problems about, for example, auctions require to use heavy homomorphic encryptions with a very large number. In general, the evaluator prover creates a straight-line computation appropriate for the problem or task at hand, then extends it by additional lines to create a total proof of the correctness of the output results, and posts split value commitments to all values in question except for the output values, and posts those on, let's say, a public bulletin board. Using that public bulletin board, anybody can verify the correctness of the outputs as a function of the still hidden, completely hidden inputs and intermediate computations. In other words, the computations all preceding the index L in the previous slide. These zero-knowledge proofs are very natural, convincing, and very tight. So one application is to secure auctions. We use the above techniques to construct auctions such that for any auction, the auctioneer announces and proves correctness of the results without revealing bid values. There are many important auctions where the participants, the bidders, do still, even at the end, want their bid to remain secret, and you can easily think about valid reasons and important reasons for that desire, not to have bid values, especially in repeated auctions, revealed to the other bidders or to the world. Now, for vicary auctions, which are second price auctions, are well known to be very prone to collusion between the bidders against the auctioneer or the seller. That was an open problem for many years, and because of that possibility of collusion, these auctions, despite their important theoretical properties, were not used in practice. Now, in 2011, 2012, and in a paper in 2014, Mikali and I solved that problem by showing that using these efficient zero-knowledge proofs, we can create vicary auctions, second price auctions, where collusion is provably avoided. Now, another application of that methodology was suggested to me by Ron Rivest, and together we then did a system of electronic voting. We used split value representations and zero-knowledge proofs to construct voting systems such that the voter privacy is provably preserved. In other words, whatever anyone voted is provably kept secret. The tallying of the vote produces an outcome verifiable by everyone, so that if the bottom line is that Al Gore won the election, then that can be actually proved in a completely convincing way without revealing any private values of votes. So my voting system with the Ron Rivest has the properties I mentioned above, and in addition, system correctness. Namely, the system is immune against any prescribed number, say 4, of gossipy and or failing vote counters. The gossipy vote counters who see the votes, but actually only components of the votes, cannot, even if 4 or fewer of them get together, they cannot reveal the vote of any particular voter. Let me add a bullet not present on the slide, that also all the incorrect votes, for example, if somebody gave 2 votes or 5 votes to one of the candidates. All of these are removable in our election electronic voting system. Used elsewhere. Lindell and Riva, and here is a reference to their paper that appeared at a very important conference, used split value representations and the connected efficient zero-knowledge proofs to achieve highly efficient multi-party computations. We are inviting further applications of this method. We are sure that many other applications exist and many people can follow the Lindell-Riva footsteps and gain wonderful results, obtain wonderful results using this new methodology. So, thank you all, and in particular Dick Karp, and see you all at the 90th birthday celebration, 10 years from now. Bye.